Hello everyone. I am Ethen Sun. I'm a PhD student at the University of Toronto, and I'm happy to be talking to you guys today about disk locking in low mass PMOs. So first, I want to say that I am an observer who does rotations. I do not do disk physics, so we're going to be looking at observations today. Okay. First, let's look at disk physics, unfortunately. So the process that we're looking at is magnetic disk locking. So this occurs when the central object embedded in a disk puts out a bunch of ionizing radiation, ionizes the inner edge of the disk, which then is coupled to the magnetic field of the rapidly rotating object in the center. This drags that material along and causes it to migrate outwards. And the net effect is that the central object dumps angular momentum into the disk and it slows down. This sets the starting rotation speed of the object and has some formation implications as well. So, I mean, this was contentious for a while, but this is the example I like to show, which is Kevin Moore et al.'s 2019 paper showing at 8 million years when disks are dissipating. If you look at objects that have infrared excess indicating a disk versus no infrared excess indicating no disk, the objects whose disks have dissipated early have had less disk breaking and they spin faster. So that's proof that this effect is occurring. So how does this change as you change the mass? Well, let's look at the high mass picture first. So what happens in protostars, for example, is that you have an accretion disk, you have material flowing inward, and the magnetic interaction drives disk wind and drives some of the material out. But the main point is that in this picture, the process is self-sufficient. The star interacts with its own disk and breaks that way. Now, at lower masses, if you look at the picture of Konstantin Batygin's model, you have a protoplanet embedded in a circumstellar disk, and its main source of accretion is material falling onto the poles from the circumstellar disk. The magnetic disk locking then causes this material to migrate out, and you actually get a decretion disk. The main difference that is physically interesting for me is that in the protoplanetary situation, in the low mass situation, you require this mass replenishment from the circumstellar disk because the planet itself just doesn't have a massive enough disk to slow it down the way that stars do early in their life. Okay, so what are the observables that we should expect? Well, as you move down in the mass sequence, you get the lower disk mass, but also you get lower radiation output and lower efficiency at ionizing the disk. And so overall, what we should expect is at some point we should see faster rotations at lower masses because of less effective disk locking. The other observable we should see is that free-floating objects should rotate faster than companion objects because free-floating objects do not have the benefit of interacting with a wider circumstellar disk, and all they have is whatever low mass disk they had initially, and so they can't break as effectively. So we should see a distribution between these different distribution between these two populations. Okay. So what does the data say? That's the title. So what does the data say? If we look at just the overall rotation of brown dwarfs, this is rotation speed kilometers per second on the y-axis. This is mass on the x-axis. We do not see this trend. The data goes down to 10 Jupiter masses or so, and we do not see a clear trend of increasing rotation speed with lower mass. Okay. As for the second observable, do free-floating objects rotate faster than companions? This is from Marta Bryan et al.'s 2020 paper. The blue objects are planetary mass companions, and the red objects are isolated objects under 20 Jupiter mass. All of these are under 20 Jupiter masses. And you can see that these are mixed in pretty thoroughly. We don't see a difference in the spin distribution of free-floating versus bound objects. Again, this is all objects under 20 Jupiter masses. Okay, so what this is saying is that this transition to less effective disk locking is somewhere below 10 Jupiter masses, which is where we have data. It's near the end of the IMF, and hopefully I'm seeing some rogue planet ears perk up now. We are in the rogue planet range, and we're looking for a physical transition here. Now, unfortunately, rotation data in this mass range is very slim pickings. To my knowledge, this is every object with a mass under 10 Jupiter masses that has a known rotation, whether it be V sin I or photometric period. There are 9 total objects here. 7 of them are bound, and I will note that 4 of them are HRA 799. So they're all in one system, which is, not as statistically powerful as 4 independent objects. And only 2 of them are free floating. That's these 2. So 2 objects, for 2 free floating objects under 10 Jupiter masses have known rotations. What I'm doing is I have gotten rotation data for 4 new free floating objects. So now instead of 7 and 2, we have 6 and 7. So this is starting to look a little more statistically appealing. We have 13 objects under 10 Jupiter masses that we can compare to the above to the 10 to 20 range that we have more data for. And we can also compare free floating to bound now. We sort of have enough to do that. Okay, just quickly tell you about the method I'm using. I'm doing V sin I with very high resolution spectroscopy. This is 45,000 resolution in near infrared, simultaneous H and K coverage with IGRINS and IGRINS 2. You take this spectrum, you cross-correlate it with a model. I'm using Sonora Diamondback. You vary the radial velocity, you vary the V sin I, and you get the fiducial values out of this. Now, I know people who do V sin I with low, like 4,000, 8,000 resolution spectra, and it comes out a little dubious. I do want to point out that this is the x-axis. This is the wavelength axis of my spectra. This entire spectrum is 14 this section is 14 nanometers wide. You could take a ruler to these lines and measure the rotational broadening, and you'll see a different example later. Okay. So this is what I measure. These are the 4 numbers that I got. 2 of them, 9.5, 15 kilometers per second. This is about in line with the previous measurements. But we also have a 35 kilometer per second and a 44 kilometer per second rotator. So out of 4 objects, these 2 are among some of the fastest rotating PMOs known. This is under 20 Jupiter masses. And yeah, that's what a spectrum looks like. Every single one of these is an individual CO or H2O line, and that's how broadened they are at 44 kilometers per second. When I was preparing this slide, somebody who knows I work on PMOs looked over my shoulder and said, "Oh, that's a cool light curve you have." You could fit a sinusoid to this, but again, that's V sin I. You could take a ruler and measure it. Okay, so let's do the comparisons and look for those observables. So I want to caution that this is preliminary. The V sin I's are fine. I mean, you can see from the spectrum, but the exact placement on this plot, and I'll explain why, is preliminary. So I've highlighted these 4 triangles are the 4 that I've measured, and I've also highlighted in green everything that was already on this plot that's under 10 Jupiter masses, and I'm just blinking them so that you can see them. So, I mean, based on this, I mean, what are the odds that you take 4 objects and you get 2 that are this fast rotating? At least based on this right now, it suggests that we are finding this transition, that below 10 Jupiter masses, objects rotate systematically faster, possibly due to less effective disk locking. As for the free floating versus bound effect, if you just look at the green objects, I say that this is unclear at this time. We can't say that triangles or the circles are systematically more rapidly rotating. And this is probably going to need a larger sample to measure because there's a lot of complicating effects. For example, you could have a free floating object that was formerly a bound object when it was doing the disk locking. And this would muddle this relation quite a bit. So the main thing I want to show here is that we have found some rapid rotators. It may be just luck, but we are seeing that they rotate faster than higher mass objects. Okay. Now for the caveats. Why is this preliminary? And it's because there are difficulties with the ages and masses for these objects. These are using the the masses and radii that come from the literature, but these are based on underestimates of their age. So these objects are actually likely to be slightly more massive and slightly smaller in radius than the literature values would suggest. Now, this isn't going to move these by a lot. It's like the error bars are going to be comparable to the other data points. I'm talking about like a 10 to 20% difference here, but that's why I haven't put the error bars up. Now, regarding the ages and masses, this is something that I'm going to continue working on using the updated kinematics we have from Gaia, for example, and the new radial velocities that I've measured. I'm finding that previous age and cluster membership attributions for these objects are not accurate. So I need to do a better age calibration on these objects, get a better mass and radius, and be able to give you error bars on this plot. Okay. So I went through that very quickly, so we will have some time for questions. This is my summary slide. I measured 4 free-floating PMOs to get their V sin I rotation speeds. I found that 2 are very rapid rotators, which is statistically unlikely. Comparing these 4 objects and the now 6 known objects, 13 known objects to the 10 to 20 Jupiter mass bin is suggestive that there is the transition in disk clocking physics and we are finding systematically faster rotators. I'm continuing to work on what these new RVs and kinematics say for ages and radii. I also want to just put it out there that I have a bunch of other projects going on. For example, I have a spin survey of the Hyades going on to measure long-term angular momentum evolution for substellar objects. I have a project on brown dwarf aurora going on, but the point I want to make is that I have about a dozen of these spectra ranging from L0 to L9, very high resolution, and I've got more coming. So if anybody wants think of something to do with them, for example, if you want to validate your models, if you don't want to do atmosphere stuff, I'm happy to collaborate. Come talk to me. Okay, thank you.
So, perfectly in time. We have time for questions.
Thank you. Great data. Glad to see you pushing the limits. Gratifying to see Kevin's paper prompting. That was nice. He was a master student with me at York years ago. I'm a little bit confused about one thing, though. Did you say that you're not expecting disk locking in free-floating PMOs?
I'm expecting disk locking to be less effective in free-floating PMOs because, unlike bound objects, they can't pull material from a larger object's circumstellar disk.
But you don't need a large object. I mean, so for example, the one that I was showing yesterday and Belinda referred to today, right? That's a 5 to 10 Jupiter mass object in Chameleon, where we see not only accretion flow, we see almost very, very strong evidence for magnetospheric accretion, suggesting the inner edge of the disk is locking to the central object. So why wouldn't that be dislocking?
The dislocking is occurring in these objects. It's less effective. So you would see a less effective version of this. Basically, if you add more material, you get more effective dislocking. Because you greatly increase the effective disk mass that you have to work with by pulling material from the circumstellar disk.
Okay, but these could have sufficiently, like let's say they have 1% of the central mass in a disk, and they have arguably they could even be longer lasting disks because the accretion rates are smaller. The disks could last a while. I'm just not convinced that the argument about less effective dislocking. But anyway.
It is a muddier effect, which I think we will need a larger sample to look at. But that's the hypothesis, is that we should, if we see this, if we observe this difference, then it would be a sign that an object in this setting.
I would predict you don't see a difference anyway. Okay. And you don't yet, I mean, in a very small sample. Okay. The other question is really interesting to see that second to last slide you flashed on the ages, trying to characterize these 4 objects you looked at with, So when you say field, does that basically mean these all 4 may not be young?
They
Or is that premature?
They have gravity markers that say they're young, but since we don't have a cluster membership for them, we're talking it could be up to 200 million years. Yeah.
So I have a follow-up question on this, because what information do you have to classify them with Banyan? Do you have proper?
So we have updated proper motions, and we have my new radial velocity, and this is what Banyan gives if you put in the new data.
Okay, so then if you have the 6D information, that should be quite precise, no? I would say.
I think you're making the point that your new kinematics are not consistent with necessarily.
It overturns these previous assumptions, which is going to change the mass and radius. Yeah.
I mean, 200 million.
That's the worst case. Yeah.
There is a lot of observation with K-peak now and IGRINS on companions. Have you included these in your plots?
So I know that paper, to my knowledge, that paper is still in review. The only one that it adds to this that's not already, like it has updated HRA 799 V sin I's, but the only one it adds is PDS 70B. And so it doesn't significantly change the sample, but it gives more precise V sin I's for HRA 799.
And there is a ton of archival CRIRES data that you should dig in, because there's a large program to measure V sin I on a large fraction of planetary mass objects. I think you should look at this data.
Yeah, so that's where this sample comes from. This is the 10 to 20 Jupiter mass range, where we have significantly more data than less than 10 Jupiter masses.
Cool, thanks.
Ethan, question here. I can't recall, but can you compare to, have you seen Kendra Kellogg's thesis paper? She did V sin I's for a bunch of objects. She found a bunch of rapid rotators. They're isolated T's.
I think so. These are like photometric, like 3 or 4 hour periods. Is that?
No, it's V sin I. It's all V sin I, and she did IGRINS as well. We can talk about it, but she found a bunch of rapid rotators, and so I wanted to know how they compared, but we can look at that together after.
I think I know at least one of them is SIMP 0136.
Different sample. SIMP 0136 has definitely been done, but Kendra's were just randos, and they were super rapid rotators.
Okay.
We'll look at it.
Yeah, let's talk about that.
More questions? So if not, I would like to point out again to the fact that you are finding so many candidates that look like really young objects, but are not classified of any of the known associations in the solar neighborhood. So profiting that Jackie is around, I don't know how you think about it, but maybe it's also a matter that we should recheck also the census in this neighborhood, because probably these are young members. I don't think they are going to be field members.
So just, if you go back to your table, you'll notice the spectral types that you had for them. There was 1 peculiar and 3 int G. Int G are our weirdest ones. So here, so peculiar PEC was always like, we don't know what's going on there. But int dash G was always confusing to us. And so the Gagne plus 15 was always just probabilities that we would have given them. Always needed the radial velocities. So this is great. We've found this happens left, right, and center. You get a radial velocity and it eliminates their kinematic potential in it. So grain of salt should always be used on these kinematic ages when we don't have full kinematics. I'm just defending a little bit what we tried back then.
It's just like the radii and masses that are derived from this end up listed in the ultra cool sheet, for example. So
yeah, it's everybody's best attempt to do things, but it's a good warning to the community. Like, take things with a grain of salt. Make sure you check why they come, because sometimes people list them.
Yeah.
And we were never saying that was the radius and the mass. We were saying this could be, but somebody needs to get a radial velocity, which you did. And these were int G, so it was always suspect.
Great, thank you. So I think we can thank Ethen again.